Rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk rainy, thunderstormy Germany. Today it's my pleasure to talk The rainy, thunderstormy Germany. Today it's my pleasure to talk. So, hello everyone. Hello from the rainy, thunderstormy Germany. Today it's my pleasure to talk to you about my research on the temporal structure of speech and language and present you with some innovative data using sensory motor synchronization and movement-based paradigms for the study of the temporal structure in speech and language. Let's first get started thinking about the role of temporal structure in speech production, perception and neural entrainment. Those are quite well-established findings that show us that speech production displays a number of temporal regularities that can be modeled on the basis of some specific time constraints. And some of those time constraints are prosodic in nature, and those regularities are quite well understood and modeled within the certain approaches to articulatory phonology. Speech perception has also presented us with a number of examples for how we exploit any type of regularity, temporal regularity in speech, in order to create predictions about what is coming up in the language that is yet to be spoken, and how those predictions can facilitate language processing. We also know from neural oscillations studies that the brain oscillations at different time scales seem to entrain to temporal regularities in speech, and those processes are known to underpin language comprehension. However, when we look at speech acoustics, we are posed with this dilemma that whatever we look at, whatever level of speech acoustics we try to investigate, there is nothing that encodes temporal regularity. There is nothing that is seemingly isochronic. So I would like to talk a little bit about this dilemma and the issue surrounding finding the regularity in speech acoustic signal. So what gives time its structure in speech? Very early approaches to the understanding of the temporal structure in speech proposed that it was the isochrony, so the temporal intervals that would be of the exact same duration. And this temporal isochrony principle was supposed to be universally applicable, and that we could classify languages with regards to which level of acoustic structure they would apply the isochrony principle to. And traditionally, two classes of languages were distinguished. The syllable-timed languages that would regularize intersyllabic intervals and basically create temporal isochrony at the level of each individual's syllable. On the other hand, we distinguished interstress intervals being regularized in languages that we traditionally refer to as stress-timed languages. And of each class, we know prototypical examples like Spanish, Italian, and French being prototypical examples of the so-called syllable-timed languages, and English, Dutch, Russian being prototypical examples of the stress-timed languages, with this dichotomy being also occasionally applicable to varieties of a language like Singapore English versus Southern British English. In some accounts of cross-linguistic rhythmic typology, we also find a third class of languages being mora-timed, like Japanese, and some other languages whose phonology relies on the time unit of mora, But the important consideration is that the so-called rhythm class hypothesis that I have described here on this slide is one of the most controversial concepts in linguistics. So, hello everyone. Has been identified as controversial as early as in today. It's my pleasure to talk to you about my research acoustic analysis, temporal structure of speech recordings, and presenting with some innovative data possible and available. This controversy stems from the evidence that we derived from analysis of production data and perception data. So the production data controversy stems from this question that we tried to answer, namely what acoustic cues give rise to the two temporal templates or the two rhythm classes. And in earlier accounts, those acoustic cues were sought at the level of isochrony of temporal intervals, syllable timing being isochronous syllables, stress timing being isochronous interstress intervals. As soon as we started being able to measure those intervals in real speech, we identified that nothing is isochronous in spoken language. Later discussions of this idea of the two temporal templates was discussed and framed in terms of the variability in the segment duration, and syllable-timed languages were expected to have little vowel reduction and simple consonant clusters, leading to low variability of vowel and consonant intervals, whereas stress-timed languages were expected to have a higher level of vowel reduction and more complex consonant clusters, which would lead to high variability in temporal intervals that contained vowels and consonants. However, this discussion has received quite a lot of criticism, and quite a few studies provided counter evidence that we cannot derive any evidence for syllable-timed and stress-timed language distinctions from the measurements of variability in segment duration. Later on, the discussion moved towards measuring variability in the duration of prosodic constituents, and it was hypothesized that syllable-timed languages would have less accentual and less phrase-final lengthening, whereas stress-timed languages would have a high amount of prosodic demarcation, which would lead to those more or less regularized timings at different levels of acoustic structure. But there is plentiful evidence for this hypothesis not being correct in terms of its acoustic substantiation. The perception data is also quite controversial in this regard. And maybe the strongest evidence in support of those two rhythmic templates comes from the experimentation with those supposedly sa reduced experiments. So one would take a spoken string of several words, and would reduce or replace all vowels by an R and replace all consonants by an S, and then let listeners judge language pairs with those impoverished stimuli as either same or different, rhythmically same or different. And it was initially shown that only languages from different rhythm classes could be discriminated if they were reduced to sa. And languages from the same rhythm class wouldn't be discriminated. However, later evidence, later experimentation has shown that this perceptual ability to discriminate between languages of different rhythm classes stems from some artifacts of speech rate differences in the stimuli. So if you normalize the sa stimuli for speech rate, the ability to discriminate between those languages from supposedly different rhythm classes also is gone. The identification experiments have been providing controversial evidence from the very beginning. So naive participants cannot use the two categories. You train them in different ways. They can't do the task. Phonetically trained listeners do not produce consistent patterns. And even phonetically trained listeners with the exact same background of their training, with the exact same native language, also don't rely on their perception of rhythmic structure, but primarily on their knowledge of the different structures that they are supposed to be judging. So they rely less on bottom-up cues to categorize spoken samples as either syllable-timed or stress-timed. My research interest and the topic of today's talk comes in with the so-called movement-based approaches to the study of temporal structure. And those movement-based approaches were originally developed to study temporal perception in music. Those approaches utilize the fact that music naturally entrains movement, which is possible due to a regular occurrence of a subjectively perceived, subjectively prominent event in time. And such synchronization of movement with music is possible even in the presence of syncopation and high levels of metrical complexity. And we seem to be genetically endowed with this ability to move to the beat of music. So here I have a video of some cute babies moving to the beat of music without being prompted, without being instructed on how to do it. They do it naturally, spontaneously, automatically as soon as they hear the musical extracts. So I'll play you a part of this video. So as you can see, babies were moving to the music with the music. They were not synchronized precisely to the beat of the extracts they were listening to. That ability develops much later in life. Only 6 to 7 year old children show a similar ability to be precisely in synchrony with the beat as the adults do. But babies have this tendency to start synchronizing to the beat without instruction and enjoying that movement in time with the beat. And that is the paradigm that we wanted to utilize in our experiments with natural speech, natural linguistic stimuli. And the first question to ask, of course, is, can we at all move in time with natural speech? There is an idea out there that language does not normally entrain movement, not in the same sense as music does. And but we also have to think about those spontaneous co-speech gestures that we all naturally use while speaking. Also head nods, eyebrow movements. All of those visual prosodic features have been shown to meaningfully align with linguistic events in time. And that is one aspect that we can think about as a ecologically valid way of looking at spontaneous movement with speech. There is also some preliminary work that looked at sensory motor synchronization with metrical speech or with nonsense words, but we wanted to move this paradigm further and experiment with natural speech, as natural as it gets. So the methods that we developed involved two tasks. In one task, in the sensory motor synchronization task, we asked listeners to listen to a sentence loop containing 20 repetitions of a sentence, and then start synchronizing with what they perceived to be the beat of that sentence as soon as they had this feeling of the beat in their bodies. And the other task that we asked our listeners to do was to experience this sentence loop with slightly fewer repetitions, and then to tap out the beat of each sentence they listened to on a loop after having finished to listen to the repetitions of that sentence. Here's an example of a sentence that we experimented with.
I wove a yarn.
I wove a yarn, which is a short 4-syllable sentence. And we had a large range of sentences and sentence durations. In the very first pilot study, we looked at sensory motor synchronization and non-synchronized continuation tapping produced by 29 native listeners of English without any known disorders and variable levels of musical training. And what we found was that there was quite a bit of consistency in participants' synchronization performance. So here I'm showing you the data of two participants, English participant number 9 and number 8. And the density plots that you're looking at here represent the aggregated individual taps across repetitions of a sentence. Our participants varied quite a lot when they started synchronizing with the sentence. Some of them started synchronizing quite early on. Usually at least 2 repetitions of a sentence were needed for a participant to start feeling the beat. Some participants started a little bit late, like from the 10th repetition onwards, they started synchronizing and producing those sensory motor synchronization patterns that we're looking at here. But what we can do in either case is basically aggregate all taps that were produced and look at the timings where participants were more likely to tap along when they were synchronizing with a sentence. So we applied those kernel density functions to tapping distributions and identified peaks. So those tiny little black dots that you see here are identified as peaks in the kernel density functions. So as you can see in the subject data of the subject number 9, we only have 3 peaks. In the subject number 8, we have got 4 peaks that were identified as such. The procedure was the following. So we first looked at the highest peak in each participant's performance. here it's the last one. In the 8th participant is the second last one. So that peak was set at the 100% value. And all peaks that were up to 40% of this maximal 100% value were considered as a peak. And as you can see here, this peak in this participant's performance didn't reach the 40% threshold. So it meant that throughout the number of repetitions, this particular participant only tapped at this particular point in time occasionally and not consistently. So if, as you can see here, there are 2 peaks in the immediate proximity of each other. And if we detected those peaks within any given 120 millisecond window, then only the highest of the 2 peaks was considered to be the peak. That was the preparatory evaluation of our SMS data. And what we looked at then was the potential targets of sensory motor synchronization. So which points in time were consistently attracting taps when participants were synchronizing with the sentences. And we considered 2 linguistic targets, vowel onsets and syllable onsets, and 3 acoustic targets, including the local amplitude maximum derived from the amplitude envelope that is shown in blue here. So we basically smoothed the waveform and just described the variability in the local maxima and minima of the amplitude envelope. And the local amplitude maximum in the syllable was considered a potential acoustic target of sensory motor synchronization. The other 2 acoustic targets were derived following the work by Sturm and Wollin, who investigated potential acoustic correlates of the so-called perceptual center in speech, or subjective moment of occurrence of a linguistic unit such as syllable. And they investigated smooth energy contours and identified the local moments of the highest maximum of energy and local moments of the fastest energy change, which they refer to as max E and max D respectively. So here is an example of the English word Friday, consisting of 2 syllables. And you can see here the variability in the location of those different acoustic and linguistic targets that we investigated. So syllable onsets consistently preceded vowel onsets unless we dealt with a syllable that didn't have an onset. Max D could sometimes precede and sometimes follow vowel onset. Local amplitude maximum and max E also varied in their position, and here in this example they follow they precede also and follow vowel onset, so they could be quite variable with regards to their timing. And what we did afterwards was basically calculating a synchronies between participants' SMS performance and their SMS peaks, and those different acoustic and linguistic landmarks that we identified for each sentence of our materials. And we basically looked at the delays between each peak and each nearby acoustic or linguistic target. Peaks within 120 millisecond window from the target were identified, and this threshold value follows previous work on sensory motor synchronization with other types of stimuli, such as metronome or music, and follows the common patterns there. And if no peak was found in the predefined window, we gave that particular landmark a 0, meaning that this landmark was not synchronized to, which we interpreted as a decreasing likelihood of sensory motor synchronization with that particular landmark. Now looking at the results of our preliminary study, identifying the best sensory motor synchronization anchor in English. So we are looking at the accuracy or the delays between the different acoustic targets and the sensory motor synchronization peaks of the participants. So here I'm showing you log absolute asynchrony that was measured in milliseconds and then logarithmically transformed. And we are looking at the different landmarks. The first one is syllable onset, followed by max E, then by local amplitude maximum by max D, and vowel onset. And as you can see, the delay between the target of sensory motor synchronization, or the landmark of sensory motor synchronization, and the sensory motor synchronization peak decreases gradually from syllable onset to vowel onset. And it is the delay is the smallest if we're measuring sensory motor synchronization with regards to vowel onset. The result is quite similar to our previous pilot experiments, where we looked at sensory motor synchronization with isolated syllables. Here we're also measuring the shortest asynchronies for vowel onsets in comparison to all other landmarks. The only difference that is a difference that is numerical and not significant, so not systematic enough and not large enough in magnitude to be picked up by the statistic that we used as a significant effect, is the difference between this max D and vowel onset. So max D, I remind you, is the moment in the energy of the waveform where you have the fastest change from low to high energy. So max D is numerically creating a numerically slightly longer asynchrony, but not statistically significantly longer. If we compare the results from the sensory motor synchronization task to the results from the non-synchronized continuation task, we find quite a striking difference between the patterns of the two tasks. So on the left, you're seeing now this sentence, I wove a yarn, that we listened to before, and the group level performance is plotted here. So as you can see, there is at the group level, there is quite a lot of consistency. So people tend to tap at 4 specific predefined points in this sentence. If we compare it to the non-synchronized continuation task, we don't find any meaningful patterning in here at the group level. At the individual level, the tapping patterns are not random. They are not completely random. There is some relationship between non-synchronized continuation tasks and the interval onset intervals as well. However, participants tend to tap more likely at the spontaneous tapping rate. So everyone performed this spontaneous tapping task where participants were not paced, they were not asked to synchronize to any auditory signal, and they were just tapping naturally at the pace that felt most comfortable to them, and using the index finger of their dominant hand. And that spontaneous tapping rate seems to be more likely to come into play when participants are not tapping in time with the stimuli of this experiment. This intention to move in time with an auditory prompt seems to be a finding that has been frequently observed across different types of auditory stimuli, and it seems to guide our perception of time in those auditory stimuli quite strongly. We also know that neural motor networks are involved in the perception of temporal patterns, and the perception of a beat seems to recruit those neural motor networks even in the absence of an actual movement. So those networks seem to support perception even in the absence of movement. Synchronized movement is also known to aid perceptual encoding of the temporal structure in complex sounds. And there is even some evidence that shows that body movement can shape how timing patterns are perceived. Let me go back. This body of research is starting to be transferred to language as well. From a very recent study by Bosca and Peters, we know that the instruction to align beat gestures with the different parts of the speech can change the perception of the word and the stress placement and perception of vowel quality resulting from it. We know that if you cue participants to tap in time with certain words, they are more likely to be better remembered, and word replacements better spotted at a later point in time. So we start to be seeing those effects of body movement on speech perception and verbal language processing. But what I want to continue talking about now is more about the synchronization patterns across different languages and how languages might differ in this regard. We studied 3 languages in our recent project. We compared English to French and Japanese. Those languages were obviously chosen with regards to their putative rhythm class affiliation that I talked about at the beginning of my presentation. So English is this prototypical stress-timed language. But the most important point about English is that it has a metrical structure, so it has alternations of strong and weak syllables, whereas French, this putative syllable-timed language, has no metrical structure. Prominence and accentuation in French is post-lexical and is a property of accentual phrases, so phrasing structures. And English and French can be compared to Japanese, that has neither, but it has the mora-based time unit and is traditionally referred to as mora-timed. So we tested 40 listeners of each English, French, and Japanese and asked them to synchronize with sentences spoken in their native language and the two other languages that they were speaking or not able to speak. I'm not talking about synchronization with the other two languages today. I'm just focusing on the synchronization with people's native language. We selected 20 sentences per language. They were matched in the number of syllables across English and French, and in number of moras for the comparison with Japanese. Here I have some examples from French and Japanese.
La marée monte. Eokaku. La marée monte. Eokaku.
So here, the English example you have already heard, I will reon, with 4 syllables was compared to French la marée monte, which has 4 syllables, was compared to eokaku, which has 4 moras, 4 syllables, 3 different unique vowel onsets, and 2 CV transitions. So in Japanese, we could experiment with quite a few things there, kind of disentangling the number of moras, the number of syllables, the number of consonant to vowel transitions. So it gave us quite a lot of scope of variability and testing the limits of the paradigm as well. Talking about the best sensory motor synchronization landmark in French. So again, looking at accuracy, here on the y-axis, you have absolute asynchrony in milliseconds that was measured with vowel onsets, local acoustic landmarks based on amplitude envelope maxima, and then max D, so the maximum speed of the energy change, and syllable onset. And I'm showing you model estimates instead of raw values as in English before. And we're comparing these 4 different landmarks in French and seeing very similar patterns to what we saw before. The shortest asynchronies were measured again with vowel onsets, the longest asynchronies with syllable onsets, and again the vowel onset has measured statistically more significant differences between local amplitude envelopes and syllable onsets. The difference between max D and a vowel onset was not systematic, even though numerically present. And in Japanese, again, looking at absolute asynchronies in milliseconds, comparing vowel onset, max D, max E, mora onset, and syllable onset, we finding, again, very similar patterns that vowel onset measured the shortest asynchronies between sensory motor synchronization peaks and local landmarks. The only difference between the Japanese and the French and English participants is that the difference between vowel onset and max D was larger and more systematic, so it was significant, which might also be related to the properties of syllable structure in Japanese in comparison to English and French, where we do find onset consonants in most syllables, whereas in Japanese, many vowels constitute a syllable nucleus on their own, and the absence of the onset consonant leads to max D being not very well estimated. So it seems like all listeners synchronize with vowel onsets. So here I'm showing you the same density plot that you saw before, but I'm also identifying the time points of the 4 vowels of this sentence, I wove a yarn.
I wove a yarn.
So the 4 vowel onsets are plotted here. And as you can see, the very first vowel of this sentence is slightly anticipated, whereas all subsequent vowels are tapped to quite precisely in time.
I wove a yarn.
Here is a slightly longer sentence as an example for French.
La côte était pleine de touristes. La côte était pleine de touristes.
And again, the vowel onsets are identified here by those lines, vertical lines. The sensory motor synchronization peaks can be seen here. And there is a difference in color in the vertical lines that are plotted. The pink lines identify vowels that have phrase level accentuation. The green ones are the vowels that are not accented. And as you can see, people tap quite precisely in time with those vowels. And again, the first vowel is a little bit more anticipated than the subsequent vowels. Yeah, towards the end, people get more precisely synchronized with those vowels. And the something seems to be going on with regards to those phrase level accented vowels.
La côte était pleine de touristes.
Japanese, a short example here.
絵を描く。絵を描く。
Again, the vowel onsets are plotted here. And some vowels are a little bit more anticipated than others. With some vowels, people don't tap as much as with others, but we do find comparable patterns again in Japanese. So we seem to find this consistent sensory motor synchronization with vowel onsets across languages. So listener synchronization is not random, it is systematic. And the vowel onset is the most likely sensory motor synchronization target, or the beat level structure in a spoken language. And it is applicable across prosodically diverse languages, regardless of their putative rhythm class. It seems that language can entrain movement in this version of the paradigm. And it's also quite clear that temporal isochrony is not a prerequisite for the extraction of the beat. So beat regularity can be experienced without any synchronous intervals. One important finding that I would like to draw your attention to is that not all vowels are synchronized with equally well or equally often. So particularly in the last Japanese example that I showed, we saw a big gap in peaks with regards to different vowels of that example sentence. And this is where we see quite interesting language-specific effects. So those are observed at the level, particularly of the SMS-like likelihood, but also with regards to signed and absolute asynchronies with the specific vowels. What we're observing in English is that lexical stress plays a major role. People tend to synchronize more and to be more precisely tapping in time with lexically strong syllables in comparison to lexically unstressed weak syllables. What is irrelevant in English is the presence or absence of the phrase level accentuation and the type of pitch accent. that those aspects of the prosodic structure do not play any role. It's really the metrical structure that is foregrounded in English. Whereas in French, what we find is that whether or not the vowel was produced with the phrasal accent, that was also kind of already indicated in the one example that I showed you before. What was irrelevant was the status of the phrasal accent, whether it was prenuclear or nuclear, whether it had rising or falling pitch. That was irrelevant for the participants' performance. What played a role was really, did the vowel affiliate itself with a phrase level accent or not? And in Japanese, moraic structure does play a role. So it does not play a role in the sense that the mora doesn't serve as a target of sensory motor synchronization, even though the mora duration was long enough for participants to synchronize with the mora. So we obtained the range of participants' tapping abilities, and we looked at how fast, if they are trying to tap very fast, how fast would they get? So, and those fast tapping rates were by far faster than the moraic rates. So participants were physiologically able to synchronize with each mora, but they didn't do it. And where mora does play a role is this bimoraic foot structure. So whether or not a vowel was part of a bimoraic foot. So bimoraiety played a role, and bimoraic feet were synchronized to more often and more precisely than monomoraic feet. The presence of a pitch accent was surprisingly irrelevant. So we might know that Japanese has a certain number of lexical items that have a lexical pitch accent assigned to them. Some words are accent-free, and we expected those pitch accents, lexical pitch accents, to attract sensory motor synchronization in a similar way that lexical stress attracts it in English, but that was not the case. So it's more about the moraic structure. And interestingly, pitch doesn't seem to play any role in this task. So whatever way we studied the potential contribution of pitch to the sensory motor synchronization, it doesn't seem to have any role to play. And all of these effects seem to be reflective of the language-specific prosodic hierarchy that carries linguistic meaning, and obviously not the putative rhythm class of the language. We also examined this idea that being a vowel is kind of a relevant issue here in sensory motor synchronization and perception of temporal structure in speech. Because vowel, if you think about it, is a phonological as much as it is a phonetic unit. So at the level of phonetics, we obviously have local sonority peaks. We have form and structure that encode a vowel. But phonologically speaking, it forms the syllabic nucleus. It's the nucleus of a syllable, which is also language specific. So some languages like German or English, they allow for sonorants to form syllabic nuclei. And what we did was we looked at a number of sentences in English where we compared sensory motor synchronization likelihood with strong, weak syllables and weak syllables that contained vowels, weak syllables that contained sonorant nuclei. And we were particularly interested in this comparison. Would weak syllables containing a vowel versus sonorant be different or not? And it doesn't seem to be the case. So weak syllable is a weak syllable, and it is synchronized with slightly less often than a strong syllable. But in a way, it doesn't matter whether the nucleus is occupied by a vowel or by a sonorant. People are equally likely to synchronize with either syllable, and to be and they are equally precise or equally synchronous or equally asynchronous with either type of weak syllable nucleus, vowel or sonorant. So it doesn't seem to be, the unique property of a vowel to induce this feeling of a beat, to induce this structuring aspect of speech. It seems to be that it's primarily the syllable nucleus that does this to our listeners. It's something that we are still looking into, specifically with regard to some languages that allow for sonorant, for nuclei to be occupied by non-sonorant and non-vocalic segments, like fricatives. So in some varieties of Arabic Berber and in Czech, we can have syllables without any sonorous elements in their nuclei. And we are interested to see how listeners or participants of those languages will be synchronizing with the nuclei of those syllables. So is it primarily a linguistic unit of a syllable structure that draws listeners' attention to, or is it just the vocalic aspect, or is it just the sonorous structure? That's something that we are currently examining. So to come back to the question that I asked at the very beginning of this presentation, what gives time its structure in speech? And in music, we know that we can understand temporal structure at two levels: at the level of the beat, that is the regular pulse that gives music its tempo, and then meter, which is a higher level structure above beat, that kind of groups beat elements together to create certain expressive temporal styles. And those are the two aspects that are key to understanding synchronization with musical signals and musical rhythms. In case of spoken language, we think that beat resides at the level of the syllable nucleus, and the syllable nucleus, it is that anchors sensory motor synchronization in cross-linguistically applicable way. It's obviously too early for us to say it's a universal, but it seems to be that the beat level structures of language reside at this syllable nucleus level. And meter in language seems to be related to the properties, language-specific properties of the prosodic hierarchy. And we're just starting to understand how those different aspects of prosodic hierarchy find their reflections in sensory motor synchronization paradigms of participants from different linguistic backgrounds. Many thanks for listening, and many thanks to my collaborators. And I will be looking forward to any questions that might arise from this presentation. The organizer of the workshop will forward them to me, and yes, I will remain available for any follow-up discussions that this talk might give rise to. Thank you to the organizer for inviting me to speak about my research. Thank you to my funders, and yeah, I'll see everyone sometime in person, hopefully soon. Bye-bye.